This conference will now be recorded.
Welcome everyone to another OCP TAP session. This is call number 80. So again, this was a relatively special one because we go bi-weekly, but then we are having this one in the middle of the bi-weekly, so the frequency doubled. And just want to also say that we're going to have the next 2 weeks also, like basically there will be another one off like the week after. So next week we have one, and then the week after we have also another one. So, and then the week after that. So like we're pretty packed. So with no further ado, I will introduce our speaker, which is our very own Kevin Stanton. So Kevin Stanton discovered the area of precision time 17 years ago while doing an evening gig as an adjunct professor at a local university. Today's topic, timing in the last centimeter, came about after he realized that since the precision time protocol, PTP, IEEE 1588, was improving time accuracy over Ethernet by literally a million %, the bottleneck would soon be within the compute system itself, like the computer itself, right? So Kevin focused and co-chaired the International Time Sensitive Network, an application known as TSN/A conference, served as a board of director, chairman of an industry alliance, and this month he celebrates his 27th year at Intel Corporation. So Kevin believes that precision time will one day be immediately available and useful to every important device in the galaxy. So I mean, I think everyone here is relatively familiar with PTM. If not, basically PTM is where you get now time not only to the NIC, like basically from the NIC all the way to the devices that are sitting on the PCIe bus, including the CPU, or pretty much to say first the CPU and then from the CPU everything else, because PCIe doesn't have a peer-to-peer thing. And it is, I think, like a very important piece when you want to get precise time in these, like let's say, quote unquote, datacom or anything that the CPU gets involved. So with no further ado, Kevin, the floor is yours.
All right, thanks, Ahmed. And yes, great introduction. Thank you very much, very kind. Yes, and I'll be motivating some of the things that Ahmed was just describing. I've given the talk, and some of you, I'm sure, attended a talk in the past where I've talked about PTM. What I've done today is I've included the core material from before, but I've also added some material in a couple of different areas that came up as questions before. And so I'll try to package all of that together, both PTM between devices through PCIe switches, and then also where does the PTM time actually come from. So we'll talk about that. We'll look at some Linux, how Linux implements that and so on. So yeah, so again, as the time synchronization inaccuracy shrunk by 1,000,000 % between systems, we realized that the last centimeters would actually become soon the bottleneck, and PCIe PTM is a solution to that, a standard solution that we'll talk about. So I'll give everyone a second to read this, and then we'll move on. So 5 years ago, I would have claimed that if you could do 1,000,000th of a second, a microsecond accuracy, you could satisfy the requirements of a broad set of applications. And what you see here is a representative of some applications that we've worked on, and where timing is a core to the application, or is becoming an important aspect of the applications in some more emerging areas. Again, I would have said 5 years ago it was a microsecond would be sufficient, but what we're finding more and more is that now that we have a microsecond easily accessible to devices and compute nodes and sensors and actuators, et cetera, people are finding new applications that are pushing the requirements further down into sub-microsecond. And so for the purposes of today, let's talk about you need sub-microsecond accuracy between devices, and let's call it tens of nanoseconds. So let's take a look at one example from since this is OCP TAP, let's take an example and a quote from someone in the world of cloud service providers. So Andrew Fikes, you can see the link here, it's a YouTube recording, and he talks about a shift to trusting time for distributed applications. And I'll just kind of briefly go through what he said. He said, everyone tells you that you can't trust time. The clock on your server is absolutely something you can't trust, and you develop this innate fear of trusting time, which is effectively legendary, especially in computer science, distributed systems. And then he goes on, I can tell you that I completely trust our time system. It's made my life so much easier having a source of global ordering that's local, that I don't have to reach out to, that I can reference locally, is a huge 3x thinking shift. And he says it took 2 or 3 versions of their database to get over that fear of relying on time. So I think this is an important point, that in the past, applications have been designed and architected around time because it wasn't there, number one, or number two, it wasn't trustworthy. What we're finding now is that as 1588 in particular has emerged and is being deployed quite broadly, it's becoming available. My prediction is eventually all the important devices in the galaxy will have immediate access to precision time. And as it becomes available, again, people find more and more applications to use the precision time. So this is the trend, and I think we're certainly nowhere near the end of that trend. So let's take another high-level view from space. Well, from space. So if we think about time synchronization, if you need authoritative time, that comes from some national time authority, and it typically goes up to, let's say, GNSS or GPS satellites, 20,000 kilometers above the surface of the Earth. It's distributed around the globe, but then it comes back down to a GPS or GNSS receiver, another 20,000 plus kilometers. And then it goes across the data center, let's say using IEEE 1588, the precision time protocol. And all of this can be achieved with, let's call it tens of nanoseconds of inaccuracy. So tens of thousands of kilometers, time has passed, inaccuracy of, tens of nanoseconds, let's call it. It's possible to do better. And the way this is measured within the data center is often with a pulse per second, PPS, and I can have my GPS GNSS receiver generate a pulse per second, a rising edge every second on the second. I can have my Ethernet NIC in my server also generate a pulse per second, and I can look at the offset between the two pulses, and I can measure some statistics over long periods of time and assess the error between these two devices and the accuracy, therefore, of IEEE 1588. So this is standard practice today, not a surprise probably to any of you. So let's take this server on one of these servers on the right, and let's zoom into that. So we have the network, the precision network time on the left, and time comes in and it's actually synchronized to the Ethernet NIC typically using a PHC. There's controversy about what exactly that stands for, but it's the hardware clock inside the Ethernet controller, which contains a very accurate copy of the network time, which is the GPS time, which is the, let's say, national authority time. But the application is up here, and the application wants to know what time it is in many cases, especially if you're doing some kind of distributed compute application and you need to do ordering, as Andrew was talking about on the previous slide. So let me illustrate this with an analogy that I don't think I've shared in OCP TAP, just to get at the difference between operating with and without PTM. So I'm up here, I'm the application, and I want to know what time it is down here, and let's call that across town, and let's think that there's some atomic clock across town, and there's a bunch of traffic, and I might have to take a bus across to get access to the time. So I send a courier from the application, and I say, please go down to across town and find out what time it is. And this courier ends up being realized in the real system as a memory mapped IO read. So the assembly code is a move instruction, let's say, and the location is mapped all the way down to this device. So the courier gets on a bus, it takes a bus across traffic, comes down here, takes out their cell phone, takes a photo using the cell phone of the accurate clock, and then instead of riding a bus, gets on a taxi, rides a taxi, and comes back through traffic, comes back to the application. And let's say that the courier left at 10 a.m. and arrives at noon with a picture of the time. The question is, based on my local version of time, which I'm wearing on my wrist, what is the offset between the watch on my wrist and the clock that was photographed? Well, obviously, if there's an asymmetry in the delay taking the bus versus taking the taxi, then there will be an error in my estimate of what time it is. Maybe the clock, the photo said it was 11:15. So I say, well, okay, let's say it was symmetrical and so on. The difference with PTM is this. Instead of sending the courier with a cell phone to take a photo, the courier actually carries a watch themselves, which is synchronized to the CPU watch. The courier goes across town, and instead of taking a photo of the atomic clock, takes a photo of their wristwatch and the atomic clock in the same photo. So when that photo comes back on the cell phone back to me in the application, I can simply look at the two times that were captured simultaneously. I can subtract them, and now I know precisely what my offset is. I can make some adjustment to my local clock so that it conforms to the precision time down in the Ethernet controller, and I can get much better accuracy that is immune to the load in the system, traffic, and so on. So that's effectively what PTM does from that's the operation of PTM, is to take a cross timestamp, two clocks captured simultaneously, which can then be subtracted one from the other. And it doesn't really matter whether the courier was to go from south to north or from north to south. The important point is that I end up with a photo that contains both clocks, single photo. Okay, so that can then be measured like before using a pulse per second out of a Ethernet controller, and there are recent CPUs that also include called a time-aware GPIO or timed GPIO that can also put out a pulse per second based on this system clock out of the CPU. And I mention that just because we have some measurements, which I'll show in a second, that demonstrate the difference when you have PTM and when you don't. So the measurements, and again, these are not new measurements. These have been presented a few times. Apologies to those that have seen it more than once. So we can measure the pulse per second offset using a logic analyzer or oscilloscope. This is ground truth with no PTM and with PTM, when the system is idle and when the system is heavily loaded. And what you'll see is that, well, two of these are good and one of them is particularly bad. So the measurements look like this. When the system is idle and you're not using PTM, when the courier is sent down to take a photo of the clock and come back through traffic, we end up with an offset of 500 nanoseconds. Now, software thinks that the offset is close to 0 and that the offset is within a couple of tens of nanoseconds. If software knew that the offset was actually 500 plus 37, it would have made an adjustment to drive the 500 to 0, but the software doesn't know. And this is one of the challenges of using a software-only method. And if because the software thinks that the time is accurate, is very, very accurate. Of course, if you did a lot of averaging, you could get this 37 down to an arbitrarily small number, which then, of course, is subject to issues like frequency changes and not being able to track those. But that's another topic for another day. Point is, we have 500 nanoseconds, which is if the system's idle, which is not terrible for a lot of applications. But if you need microsecond or sub-microsecond, things get worse when you add system load. And here we see thousands of nanoseconds potentially of time error. And the biggest problem with this blue line, no PTM, where the system is loaded, is that the average increased. So now when you do long-term averaging, again, you'll think that you're doing well because the average error, the jitter goes down, but the average is still well above, in this case, above 1,000 nanoseconds. With PTM, the story is pretty nice, and we're down at sub 20 nanoseconds, let's call it, independent of load. So if the system is loaded or not loaded, you end up with effectively the same. And there was a longer presentation by myself and several others from the industry, including NVIDIA, formerly L. Mellanox, at this link down here. There was a PTM webinar as part of OCP TAP. So I just included that there, and there are other measurements from others that show similar numbers with different systems. If we zoom in, you can see the PTM based measurements. Again, this is ground truth. This is using a hardware measurement of the system time at the CPU versus the network time that's in the NIC, and all based on hardware. But software is, of course, in the loop with making adjustments. But the hardware is making the measurements, and the hardware is putting out the pulse per second. Okay, let's turn then to how software is involved. And we're going to talk a little more about the TSC than I have in the past. So I'll mention that. So Linux, for example, disciplines time. And typically an application, if they want to know what time it is, they'll call clock get time. And if you want to know what is the real time, you put clock real time, and you'll get basically clock monotonic plus leap seconds plus nanoseconds since 1970. Clock monotonic is an adjusted version of the clock monotonic raw, which is basically the CPU's timestamp counter, which is an instruction in x86 converted into nominal nanoseconds. So any call to these functions results in an instruction, read the TSC, which is very fast, some scaling, and then this M and this C, which correct for the local frequency offset of the local crystal, and then add the offset of nanoseconds since 1970. And then the M is adjusted periodically by Linux based on something. The something ends up being PTM if you have it, so that this clock real time gives you the GPS or the national lab time, if that's where the grandmaster is coming from. So this all-important measurement is shown here on the bottom left, where what you want is to be able to subtract the current time according to this equation and the current time according to PTP. In order to do that, you need an estimate of what are those two at some point in time. And as we used in our analogy, this is either done in software by asking a courier to come down and read this, take a snapshot, or with PTM by simultaneously capturing them both in hardware. And then that pair is used to discipline or adjust the M so that the difference between PTP and clock real time goes to 0. That's really the goal. Okay. The good news is that if your hardware supports PTM, both the root port and your PCIe device, then down inside of Linux PTP, when this ioctl, when it wants to make this measurement, it automatically appends the _precise to this the PTP sys offset, and this asks the driver to ask the NIC to make the measurement using PTM, and you have great accuracy. If you don't have PTM, then you fall back to the legacy PTM sys offset, which uses the courier without this wristwatch, without the hardware cross timestamp, and then you get what you get, which can be subject to system load. I'll also mention that there's nothing here that needs to degrade when you have a hypervisor in the path, because the snapshot is really capturing the system time with respect to this TSC. We'll dig into that a little bit later. And the PTP time, and this measurement is not dependent on going through. There's no critical section, I guess, in software that would potentially involve a hypervisor. So there's no need for this to be inaccurate when you go through when you have virtualization. Okay, let's look at how PTM works then in practice. So before we had the CPU in blue on the top, we have the NIC in yellow on the bottom, and what we want is a cross timestamp down here, a pair that is captured simultaneously. And here's our PTP time. This has been synchronized through 1588 or whatever to the source of time that we care about out there on the network, maybe a GPS receiver. So PTM is defined such that requests go north and responses come south. Again, this was just an arbitrary decision, but it doesn't matter as long as we end up with this cross timestamp at the end. Responses can have data or not data. The first response here has no data. Subsequent responses have data. The data they carry are shown here. So just like in PTP, you end up with a 4 timestamp two-way exchange. I make a request, and in the NIC, using some counter, it doesn't matter what the counter is, I capture a T1. When the response comes, I capture a T4, then T1 prime, T4 prime. On the CPU side, I have a T2, T3. Now these are with respect to the system time. And that is important because the T2 from here is actually communicated, and the T3 are communicated in the next response. T2 prime is communicated here. So what do we do with these things? Well, first of all, we can measure some durations, T3 minus T2, T4 minus T1. And what we want to do is get the system time and the PTP time captured simultaneously. So the equations look like this, and they're pretty straightforward. So at T1 prime, the Ethernet controller captures the PTP counter, the green. So at T1, when we send this PTM request, we capture the PTP counter in green. Now what we want to do is populate the blue with the associated time up here. Well, we're going to have to use some simple arithmetic to do that. What we first do is we compute the link delay. The link delay is this. How long does it take to get from a transmit to a receive? And this is a speed of light. There's nothing in the way here. This is just wires, traces on the board, but we should measure it. It's pretty simple. It's this difference minus that difference divided by 2. Basically, it's this time minus that time. That gives you the round trip, and then you divide by 2, you get the one way. So the link delay is pretty easy to calculate. Once we know the link delay, we can take the T2 prime, which is this number, and we can back it up by 1 link delay. And now we know the CPU time at T1 prime, which is the time we captured, at which we captured the PTP time down here into the green. So we can populate the blue with T2 prime, which comes back in this message. There's the T2 prime, it comes in the response. And subtract the link delay. We have all the information we need to calculate the link delay. We calculate it, we populate the blue. Now we pass that back up to the driver, and the driver returns the value. It does the conversions, and we'll look at that in a second, and returns PTP time, that's the green time, and clock real time, which is the TSC associated with the blue converted into clock real time using the coefficients we show on over here. Okay, before I move on to the switch, if there's a PCIe switch in the way, which is something I've not presented at all before, are there any questions about this particular slide? This is a key slide. Would anyone like to unmute
Yes.
and ask anything? Yes.
Okay, Kevin, can I ask a question? So
Please.
you're saying that the first PTM response doesn't have the data, but the second one has the data. So is it always the first and second, or is there some timer? And
Yeah.
after some time, we're saying this is a new session or something like this.
It's a great question. We don't have T3 minus T2 in at this time. When we first send the first response after reset, we don't have any data, and so we just send a response. When we have the data, we can send T3 minus T2 from the previous one. So it's really just an initialization step, but there are also cases where, for whatever reason, maybe the root port doesn't remember, doesn't trust the values from before. I'll make up a reason. Maybe the link speed changed, and the method of measuring this is different, or maybe, right? So there may be other reasons why the PTM response without data might be sent later, but during normal operation, you should only need one PTM response without data, and the rest can have data.
Hi, Kevin.
Yeah, the second question is, so is this a periodic session that just all the time we have these PTM messages, or only when the client would like to know what is the snapshot of the time you will do this process?
Good question. When does this happen? According to PTM, it happens whenever necessary. The device decides when it needs to do a PTM. If you have a NIC, because PTM is obviously a general protocol for any kind of device. If you have an Ethernet device and you've implemented PTP, and you're using Linux and probably other operating systems, then this will trigger a PTM request typically. So for Ethernet devices, if you look at them in practice in the real world, they issue a PTM request at least when this is when this ioctl is called down to the driver, sent down to the driver. But there could be other reasons why a device would want to unsolicited generate another PTM request, and that's certainly allowed.
Thanks.
Yep. Other questions? Was there someone else?
Yes. Hi, Kevin. What's the mechanisms inside the CPU to generate the T3, T3 prime, and so forth, the response back to the NIC? Because in the previous slides, you mentioned that this is agnostic to load and system. So I'm just wondering the mechanism that's generating these responses back to the NIC.
Yeah, it's a great question. So for this to work, the T2 prime here in particular, this T2 prime that is sent back in this PTM response, software needs to convert that T2 because it's going to be placed in this blue box in a register. It's going to be passed back to the driver, and the driver has to convert that, or the OS and driver and Linux PTP somehow somehow that T2 prime has to be converted into a clock real time. And again, clock real time is the TSC scaled to nominal nanoseconds times this M that's changing periodically plus some constant. We're going to talk about that in a couple slides. But it's a great setup for where I'm going in about 3 slides.
One more thing, Kevin, isn't this like a disadvantage that the T3 minus T2 is considered with T2 prime, because there is an assumption that basically that there is a consistency basically between when T2 arrives, when basically request arrives, and then when you're sending response, or that is all by hardware and is always constant.
Yeah, it is an assumption. You're exactly right. We assume here that the link delay is constant. And because yes, we assume the link delay is constant because the way PTM is defined, if there's something in the way, in the path, that might have a variable delay, we assume speed of light is constant, you know, plus or minus, temperature and expansion of the traces on the board. If there's something in the path, then it will be responsible for correcting any additional delays that it inserts, so that at the end we can still trust that T3 minus T2 is the same as T3 prime. I'm sorry, T2 minus, well, I won't do the math. The time it takes for the message to pass in this direction is the same over time, and it's also symmetrical. That's right. We assume those.
So for that, from the NIC's perspective, you already have T1 and T4 from the previous session.
Yes.
Wouldn't it be useful that you basically wait for the second session, which is basically now you have T1 prime, T4 prime, and then you got also the T3 minus T2. So when you do the calculation, that like basically in the NIC, you actually use T1 and T4, which they were available from the previous session. Yeah, you will have a PTM correction with 1 second lag, but you will have the highest precision because you're dealing with the whole calculation with T1, T2, T3, and T4.
Yeah, I hear what you're saying, and I agree. This link delay, there is opportunity to make it not just, there's opportunity, as I show it here, it's an instantaneous measurement from the previous dial-up, right? Just like a P delay measurement for peer-to-peer transparent clocks in IEEE 1588, you could average this, right? You could do something a little bit smarter that would reduce the jitter caused by the timestamp granularity of the individual measurements, and the LD would get closer and closer to the true value.
Yes.
Yeah, that's right.
And then last thing, there is also, I mean, similar to E2E and P2P. Is there something similar here you can do?
Sorry,
like you know the two schemes, like the E2E versus P2P, right?
Yes, yeah. End-to-end peer-to-peer, yeah.
Yeah, so like for example, some of these things you can consider them stable, and then I don't know, I'm just wondering.
Yeah, what we tried to do when we defined this in the PCI SIG, we tried to remove as many options as possible, because my opinion was and is that there are too many options in 1588. So
That's right.
if we could have one method that would work for all cases we could imagine,
Yeah.
for example, PTM requests always go toward the root port. Well, that's that actually we couldn't think of a case that you could not solve with that simplification.
Yeah.
So we tried to make all of those options go away and just have a single approach.
Yeah.
Which brings me to the switch. If I can move on to that.
Yeah, let's go next.
Okay. So this is a new slide, and this is meant to be representative, not necessarily exactly how every implementation would work, but to show an example of how a switch can compensate for the delays. Because of course, these PTM requests, while their speed of light very constant over a wire, through a switch, there's buffering and clock crossings perhaps, and so on. So we need to compensate for that. This is actually a diagram from that went into the PCI PTM spec. So you have your root port up here, you have a switch, you have another endpoint, and maybe other endpoints, and maybe other switches in the full hierarchy. But let's just take a look at a single switch in between an endpoint and a root port. So up here we see the diagram we just looked at. So the endpoint needs to think that it's talking directly to the root port like before. So the switch's responsibility is to make itself appear invisible from the perspective of the timing. And what I've shown on the left is only the relevant pieces. So I tried to declutter the diagram. You can look up here and be reminded of the 1, 2, 3, 4, and so on. So as before, the endpoint sends a request northward. And then as a result, a switch can send a request northward itself, which results in the T2 prime like before. And the T2 prime comes back down in the response like before, because the root port doesn't know that there's a switch there. It just responds. It's a responder. So the challenge now is when the switch responds down to the endpoint, what does it put instead of a T2 prime, because that's no longer valid. The T2 prime was here, and we have a link delay, which was used before by the endpoint up here. The link delay was used. So the switch knows the link delay northward, but there's also this other delay, this D, from receiving the request to sending the request, that if it's measured, we can tell the endpoint, hey, the T2 effectively was, the T2 prime was T2 prime, which is here, minus a link delay, minus the D that we measure. And now we've corrected for the extra delay that we've inserted into the time and the extra link delay that we inserted. So to summarize, the endpoint sends a request, the switch sends a request, the response comes down, and then the switch can correct for the T2 prime to take out the upper link delay and take out the extra delay in between the receiving and sending a response, or sorry, the PTM request. Okay, and so in this way, all of the switches in the path basically correct for the upstream link delay and their own delay, and we can maintain maintain the accuracy. Now, while there are CPUs and multiple endpoints from multiple vendors that implement PTM, as you'll see in a few slides, there's OCP TAP has a web page that shows devices that support PTM. There may be some switches, Julian will correct me, but the switch availability has not been announced pervasively at this point for PTM. So this is how it will work in the future. Any questions on this briefly? I think I've got 20 minutes. I do have some more material. Let me keep going. So this this delay D here, if my clock that I use in my switch has a frequency error compared to the PTM route, then I will measure this D incorrectly. And that's always the case when we're measuring duration, elapsed time. This is particularly bad, or can be particularly bad, for PCIe devices because of spread spectrum. Let me just briefly talk about spread spectrum, and this might be a deeper dive than you're interested in. I'll keep it kind of brief. So in order to reduce the peak RF emission, especially over traces on a board, often the clock will be downspread, like 0.5%. So instead of running at some nominal frequency, it'll run at an average of 0.25% slower, and then it'll be sinusoidal. Yeah, this is piecewise linear, but you get the idea. Sinusoidal, modulate the frequency so that you take a spike in RF energy and you spread it out over so that you can pass the FCC requirements. This has two implications for timing, excuse me, over PTM. Number one, if a switch is getting a spread spectrum clock, then it's measuring that D duration at a rate that's 2,500 parts per million slower than it should. And there's also this area here where it's going all the way down to 0.5% below. Then it corrects it, then it ends up being zero average, but you might be sampling somewhere in here. And we can calculate that ends up being 2,500 microseconds per second of error, and plus or minus some let's call it 20 nanoseconds of jitter. Now the measurement of D is perhaps much less than 30 microseconds, and so you'll end up with just a fraction of this area that'll be accumulated, all of that. But just to say that this is something that should be compensated for, really, in a switch or anything that's spread spectrum clocked, because if you know that you're down spread 0.25, then you can certainly correct for that when you're measuring time. And there probably is even something you could do about this, but that's certainly more deeper than we want to go today. Okay, and that's maybe a little bit too hardware deep dive, but so let me summarize what we've talked about so far, and then I'll go a little bit deeper dive into what was asked earlier about the CPU clocking and timekeeping. And I see we have 15 minutes. So time's distributed with precision around the globe today. We have GPS, we have PTP, and we can get uncertainty down into the tens of nanoseconds over large distances. But within the last centimeters to a server, it can be substantial, and that can be relevant for a lot of applications. Now, PCIe is a standard feature, or sorry, PTM is a standard feature of PCIe, but it is optional. And some hardware already has it, some hardware is yet to have it. Speaking from Intel, there's a number of devices that have PTM today, including the latest Xeon. And with PTM, you can get synchronization accuracy without that's immune to load. And this is the chart, and there's the link to see the list that's maintained of it's crowdsourced, I guess. If you request it be added, you can send an email to Julian in particular is maintaining that. Okay, so let me do a deeper dive into, which has not been part of the previous presentations, a deeper dive into how that PTM time is derived. So with PTM, we measure the time difference between Ethernet and CPU. The question is, where does the PTM time come from, and how is it related to the TSC? So the TSC was introduced, I think it was 1990 in the Pentium 60 megahertz. That was a long time ago. And it was defined to run at the 60 megahertz. So it just ran along. And there's been a long history when the frequency could change over time, or there were multiple CPU cores, and there was an evolution of it. But in the end of the day, there's an instruction, read TSC, timestamp counter. And it runs at effectively the max non-turbo frequency of the CPU. And you can actually try this for yourself on Linux. If you go to this directory and you cat the available clock sources, you'll see TSC, hopefully, and some other potential clocks, maybe the HPET as well. And then you ask for the current clock source, and mine happened to be the TSC when I ran this yesterday. Notice that the current clock source is a writable file by root. You can actually cat, or I guess echo, some other option into this current clock source, and you can actually change the clock source on the fly. And what you'll find is, if it's not TSC, your clock get time call will be substantially slower than if it was TSC. And you can even read the TSC if you want from Windows or Linux. There's some intrinsic that puts the assembly in there, but usually you don't have to do this. You want to use the clock get time and the POSIX higher level calls that convert this TSC, which is just free running, into something that relates to time that you care about. Now, a nuance is that the TSC was redefined. This is the software developer's manual you can see here. So all of this is public information. Invariant timekeeping. So the invariant TSC is basically this ART value times a ratio plus a constant. Now, the value that comes out of this turns out to be very, very close to what it would have been if it simply ran at the max non-turbo frequency, but it's formally defined this way. So notice this ART value here. And so the question is, what is ART? ART runs at the core crystal clock frequency. So that would be, say, 25 megahertz, for example. And these M and N that you multiply and divide by are part of discoverable by the operating system. And it starts at 0. So this is a redefinition that was put in place a little while ago. And if you look into the Linux kernel from Arch x86 Kernel TSC, if you're into timing, you should definitely take a look at this tsc.c. It's quite interesting. There are a couple functions. One is convert ART to TSC. And the other one is convert ART nanoseconds to TSC. And actually one follows directly after the other in the Linux kernel file. So the thing I didn't mention before is that the timestamps, maybe you picked it up, but the timestamps for PTM, according to the definition of PTM, are in units of nanoseconds. We don't want to have to communicate clock frequencies and so on to PCIe switches and endpoints. And so it's the timestamps T1, T2, T3, T4 are always represented and sent and encoded in those PTM messages in units of nanoseconds. So this particular function right here, convert ART nanoseconds to TSC, is something that is then used to convert, and you'll see that this function is actually called in the Linux kernel in the PTM context. So at the end of the day, the PTM time, which is answering the question from before, and this you'll see this in any driver that implements PTM, it calls this function to convert the T2 prime subtracting the link delay, which is stored then in that blue register. It converts that into the TSC, and then once you have a TSC, now you're home free. You can get all the way back to the POSIX clock real time. Now, I don't remember the name of the person that asked me that question when we were looking at the POSIX clock get time, but does that answer the question you asked way back then, 15 minutes ago? Whoever that was. All right, I'll take that as the question was answered. So putting all that together, effectively you have a core crystal clock. There's this ART which runs from that according to what we just looked at, two diagram picture slides ago. You have a multiply add, you saw that in the text, plus the K, and that's the TSC. The ART is converted to nanoseconds, and that's what's used by the root port in order to generate the T2, T3, which are then passed in units of nanoseconds back to the device. Now the device has the blue and the green timestamps and can convert back to the clock real time. Okay. So in closing, I just wanted to talk a little bit about future. And all of this is in order to give an application a number which corresponds to now. Clock real time is only a now thing. So that's the current time. But I'm seeing in certain industries a need to also represent how certain are we that now is actually now. So wouldn't it be nice if you could also be told, I'm 99.999% certain, that's 5 nines, with 5 nines of certainty, the time that I gave is inaccurate to less than 27 nanoseconds. It's within, let's say, plus or minus 27 nanoseconds of the value I gave you when you asked for the time now. And also, with respect to whom, let's say NIST, or maybe there's some local time source for a small cluster where I don't need it to be TAI, I just need it to be synchronized among some small group of devices, for example, in an automobile or in a spacecraft. And in the case where the devices are perhaps not physically isolated from potential bad actors, I've also authenticated that the time source, actually the time came from the source that I reported to you some amount of time ago. So these are other dimensions of time and the ability to know what the accuracy is, know to what degree you can trust the accuracy, and that it hasn't been tampered with on the way. Any questions, thoughts about this?
I do have a question. Does IEEE 15AA spec define the minimum requirement for the time accuracy down to like 20 nanosecond level, or does it something like that?
Yeah. It really doesn't. It's more about the protocol. What is the protocol? What's the format of the messages that are sent? And it's up to an implementation to achieve certain level of accuracy, and a deployment, actually, and the integration of multiple systems. No, 1588 does not even require you to do hardware timestamping. You can do software timestamping, which is subject to all of that stuff we talked about before, plus all of the jitter across the network. If you are forced to do that, you can also, but of course, then you get what you you get what you engineer. If you don't have any clocks in the network that support PTM, then you'll be degraded. Your time will be degraded. Anything else? Any other questions on this? All right. So
just one question about the future.
Yeah.
Since there is also an EPTM specification which requires some minor changes, like invalidating some of the TLPs, is that required also on the platform part or only on the endpoint part?
Yeah, it's a great point. If you look, I can tell Maciej that you've dug into the PTM spec itself. So the PCIe spec. Yeah, there was a race condition that we found some time ago. It was some number of years ago, because this was implemented, for example, in an Atom chip for IoT applications 5 years ago, 6 years ago. Anyway, there was a race condition where with retransmissions, there could be some uncertainty about which request was being responded to, I believe. I think that was it. It's been a while. And so an ePTM, as you just mentioned, enhanced PTM was defined to remove that ambiguity. I'm not sure, but I suspect that all the devices out there in the last couple of years certainly have implemented that. But you asked a different question, Maciej. You asked, does the root port implement as well as the device? Honestly, I don't remember. I don't remember which of if it was one or the other or both.
But the platforms that were released recently should support that, right?
Yes, that's right.
Okay.
There was also another fix where there was some confusion on the implementation of one of the fields in the TLP, the PCIe message, of the endianness. And it turned out that it was a pretty common misunderstanding of the specification. And so there's also a feature which allows you often to flip the endianness so you can work with older devices, and also to discover, and also a clarification about the correct endianness. So that was also discovered and corrected some time ago.
Okay, thanks.
Yeah. Okay, so as Ahmed said, I think the universe is maybe a little bit too aggressive, but at least in the galaxy, we should be able to get time synchronization to all the important devices. And here's a presentation by NASA talking about their interconnect for future devices. And here they include AS, and what they mean by that is 802.1 AS, which is a profile of 1588 for cyber physical systems, automotive, industrial, aerospace, and so on, audio, video as well. So we can look forward to precision time, at least in the solar system, and maybe beyond in the near future. Any other final questions? I think we have 1 more minute.
Can I ask a question?
I do have.
Oh, sorry.
No, we'll go. And then we'll go next.
So I have one question. That is, you mentioned that some application is may not be satisfied with microsecond accuracy. And what would that be? Can you give us examples?
Yeah, so there is, in multiple industries, there is a push to do sub-microsecond, for sure. Within OCP TAP, it's been commonly discussed down to 10 or tens of nanoseconds that would be useful. And then also in other industries, industrial automation, for example, they need 1 microsecond, worst case, end-to-end over the entire network. So that's the entire chain, and that's up to 100 hops, I think. So yeah, the need for sub-microsecond is much larger than I expected 5 years ago, and I see it growing.
So I mean, one point is that, like, for the industry automation, I thought the switch jitter would limit the needs to be 1 microsecond, but you are saying the 100 chains of the link might sort of require the tens of nanosecond accuracy to achieve 1 microsecond end to end. Yeah,
if you divide up the budget of 1 microsecond end to end, and if you wanted to look more, there's a IEEE 60802, which is a specification which goes to those kinds of applications.
Thank you.
Yep. Someone else had a question.
Eric. I think it was Eric.
Yeah. I think my question was somewhat answered by the previous questionnaire. So
Okay.
Any more questions? So the one last question I want to clarify. So the link delay is calculated from T1, T2, T3, T4, but then we take the link delay and we use T2 prime to calculate the correction basically.
Yeah.
So yes, like the PTM root time at T1 prime. Why don't we simply just use T2, so T2 prime, and aim for T1, and you just have like 1 second lag, but you're not making an assumption of stability in the system.
Yeah, you could absolutely do that. And this is an example implementation. PTM doesn't tell you that this is what you should do, and you would be welcome to timestamp back here.
Yeah.
The timestamp the NIC counter, and then over here compute what is the do another PTM request, and then you could certainly do that. If you don't trust that the link delay is constant, then you should do that. But if you have a reason for the link delay not being constant, then you could generate 2 PTM requests back to back. And
like
not even wait very long.
But this, I think, it will be a simple, like what I'm looking for will be just like out of curiosity. Would that require the driver to do this? Because the driver is gonna, with Yoctl, is gonna give me back the PTM root time at T1, right? Do I need to patch the driver, or that will be part of PC2Sys?
Yeah, it depends on the implementation of the hardware. If the hardware captures T1 and T4 and the values coming in the PTM response, then the driver could do all the calculations. If the driver does this calculation, if the hardware does all the calculations, then of course it's a hardware change. If the hardware simply makes those values available to the driver, then the driver could do whatever it likes and could say, do a PTM request, do another PTM request, have all the data, and then do the calculation, whatever calculation it likes.
But in ordinary implementation, you get that from Yoctl, from the driver. So those two equations, they run basically on the NIC's processor, right?
It depends on the NIC. So the implementation of whether this is in the driver or in the hardware is hidden by the driver. If it's in the
that's not what I mean. I mean it's behind the driver. It's not like in the OS. It's not in the user land.
Right. It's from the driver.
I don't care. It's like in the driver or in the hardware, but it's hidden from me in user land.
Yeah, the driver has an API that returns you to timestamps, and that's it.
Yes.
That's the interface. So.
That's right.
All right. And maybe one last question. Let's say future works. If you want to add, like, what are you compromising here? Let's say if you had a magic stick, like what would you do? Like, what would you put here as a wish, like to take it to the next level?
Yeah, well, the obvious next steps are as it relates to PTM, is the accuracy. That's a knob that you can turn. It's granularity. It's in that diagram, right, that Julian is maintaining here. It shows the granularity that's reported. So that's an obvious one. Is if there's a need for better granularity, then implementations can achieve that and then advertise it in their config space. I think that the rest, the other things are that are interesting are about accuracy, reporting, estimating the accuracy, like I talked about the future, and security, especially in unsecured environments.
Yeah.
So that if there's an attacker that's in the path that's adding delay in the network, for example. Now I'm talking not just PTM, but PTP generally. Or yes, that could be detected. And 1588 has a security section. There's a couple of TLVs, type length value. There you can protect hop to hop and end to end. I think that's an important and pretty straightforward direction. But then when you have devices that are not participating and you have end-to-end clocks, for example, that's another challenge again in systems that are not physically secured. So it's not just the accuracy. I think it's those other aspects of making the time useful so that applications knowing, for example, that the inaccuracy is increasing or that the number of nines of certainty is decreasing could do something else in the application as part of their application logic.
Thank you. Any more questions?
Yeah. So for any vendor who design a timing card that used on the server or any computing device, right? Is there an industry standard that require this timing card to be accurate down to how many nanoseconds? Is there an industry standard?
Not yet, but there is the 3335 standard, which may or may not specify a minimum accuracy. But I think that's still a work in progress, but that's where it would be defined if it were to be defined.
Yeah. I mean, as
all right,
preliminary to that, we have if you go to ocptap.com, go to the wiki, we have a document that was prepared by Gary Gerst from SciTime that has specifications for different, let's say, time appliances. But in terms of application, as Kevin said, that's a work in progress in 3335.
So I'll leave you with an ode to PCIe PTM compliments of 4. I think it does a pretty good job, and I hope you can get a couple laughs out of its view on bus to bus and card to core, timings match evermore, etc., etc.
That's amazing. All right, any more questions before we close off? And again, as you know, like this already recorded, so you can watch it, and perhaps you can reach out to Kevin as well if you have any questions. And if more, go ahead.
So if we have the time, it's in the details. But if I remember correctly, the specs, there is local time invalidation event, right? So you can save the context for amount of time. And I was wondering, what was the consideration when setting these timers? I mean, for how much should the context should be validate?
Yeah, it's a great question. You know, what I'd suggest is the PCIe PTM spec, like 1588, but not like 1588, is pretty flexible. You can implement with a very large range. The dynamic range of the accuracies you can achieve is quite large. And if you have certain platform assumptions that you're making, like spread spectrum, there are certain things you should and shouldn't do. And those considerations, it would be good to walk through and document some recommendations about that. And maybe that's something that OCP could take on just to clarify where it matters to the end-to-end overall accuracy. I think that would be a useful exercise for OCP TAP to take on.
Yes, for sure. Noted.
Thank you.
Any more questions? Great, hearing none. We'll see you guys next week. Bye, everyone.
Thank you. Bye-bye.
Thanks,
Thanks,
everybody.
bye.
Thanks.